Welcome to the Deep Dive. We're here to unpack complex topics, giving you the essential insights you need to be, well, truly well-informed.
And today we're tackling a big one, artificial intelligence.
That's right. Our mission is to take a deep dive into AI, really guided by the thinking of one of its key figures, Geoffrey Hinton.
The godfather of AI, as he's often called.
Exactly. We've gathered a whole stack of your sources, interviews with Hinton, excerpts, and also that foundational text, The Deep Learning Revolution. So the goal here is to trace AI's history, pinpoint those breakthroughs that got us where we are today.
And explore what the future might hold, according to Hinton himself.
It's quite a story, and it really starts, doesn't it, with a kind of fork in the road.
Yeah.
Two different ways people thought about building intelligence.
Absolutely. It's fascinating. Looking back, there were these two main schools of thought, fundamentally different approaches.
Okay, so let's paint that picture. What was the first camp?
Well, on one side, you had the logic-inspired approach. We often call it symbolic AI.
Symbolic AI.
Okay. Yeah. And this approach, it really prioritized reasoning, explicit reasoning over learning.
How did that work in practice?
The idea was you build intelligence by feeding it symbolic rules. You know, like programming and logic. If X is a human, then X is mortal.
Right, like basic logic class.
Exactly. So you tell the system, Socrates is human, and it can deduce, therefore, Socrates is mortal. It's all about explicit knowledge deduction.
Makes sense on paper. But you said it hit a wall.
It hit some pretty significant walls, yeah.
Right.
Because, well, the real world isn't always neat logical rules. It's messy.
Right.
So projects like Block's World, trying to teach a robot to just stack blocks, they became incredibly cumbersome.
Just stacking blocks. Why was that so hard?
Because the number of rules you need just explodes, you know? Don't put block A on B if C is already on B, but then what if D is next to C and it just gets out of hand? Too many exceptions, too much context needed.
I see.
And then there was Psych. Hugely ambitious project trying to codify all of human common sense.
Common sense. Wow, how do you even start?
Well, that was the problem. How do you write a rule for dropping a glass will probably break it? Or, you know, eating soup with a fork isn't a great idea.
Huh, right. It's intuitive for us, but hard to write down.
Incredibly hard. These subtle, context-dependent things, they just don't fit neatly into logical formulas, so that approach had its limits.
Okay, so if that rule-based way struggled with the messiness of reality, what was the alternative? The other path?
The other path was biologically inspired connectionism, or what we now mostly call neural networks.
Neural networks, the term we hear all the time now.
Exactly. And this approach flipped the priority. It emphasized learning over explicit reasoning.
Learning from data.
Learning from data. Instead of programming rules, you build these networks that adjust their connection strengths, their weights based on examples. They learn the patterns implicitly.
But you said this wasn't always the popular approach.
Oh, not at all. Quite the opposite, actually. Back in the 1970s, neural nets were deeply unfashionable. Hinton himself mentions his PhD supervisor actually warned him against working on them.
Really? Why?
Worried it would be bad for his career. It was seen as a bit of a fringe idea, maybe even a dead end by many.
Wow. So he really had to persist.
He did. He stuck with this less traveled path.
Okay, so persistence pays off. There must have been a moment, an aha moment, that really shifted things for this neural network approach.
There absolutely was. A pivotal breakthrough really popularized by Hinton and others around 1986. It's called gradient descent with backpropagation.
Backpropagation. Okay, that sounds technical. Can you break down how it works? In simple terms.
I'll try. So imagine the network makes a mistake. Say it sees a cat but calls it a dog. An error, right?
Right.
Backpropagation starts with that error at the output. Then, using calculus, specifically the chain rule, it works backward through the network, layer by layer.
Backward.
Yeah, back toward the input. And as it goes, it calculates something called the gradient of the loss. Essentially, it figures out how much each connection, each weight, contributed to that mistake.
Okay, so it assigns blame, sort of?
Sort of, yeah. It pinpoints responsibility. Then comes gradient descent. You adjust each weight, just a tiny bit, in the direction that reduces the error.
How does it know which direction?
That's the gradient part. Think of it like a ball rolling down a hill. The gradient tells you the steepest downward slope. You nudge the weights down that slope, gradually making the network better.
Okay, like tuning an instrument bit by bit.
Exactly. And crucially, it does this for all the weights in parallel. It's way, way more efficient than just randomly tweaking weights one by one, which would take forever.
Right. That makes sense. So the network adjusts its weights to reduce errors. But what is it actually learning when it does that? You mentioned feature detectors.
Yes, that's the really cool part. As the network trains these hidden units, the neurons in the middle layers, not the input or output,
Uh-huh.
they start to spontaneously organize themselves into feature detectors.
Meaning?
Meaning, in something like image recognition, the early layers might learn to detect simple things. Edges, curves, maybe textures, basic building blocks. Then layers deeper in combine those simple features. They might learn to detect more complex things like, say, a bird's beak or a wing or a foot, object parts.
Ah, so it builds up complexity.
Exactly. And eventually, these complex feature detectors feed into the final output layer, which might activate the neuron for bird.
And you mentioned this mirrors biology.
It does, remarkably so. The structure is quite similar to the hierarchy Hubel and Weasel found in the visual cortex of mammals. Different areas processing increasingly complex visual information.
That's fascinating, a kind of convergent evolution between biology and this computational approach.
It really seems that way. But, this breakthrough didn't instantly lead to the AI spring. There was still that AI winter.
Right, you mentioned Minsky and Papert's book Perceptrons in '69.
Yeah.
That really put a damper on things.
It did. It showed the limitations of very simple single-layer networks, and many people just gave up on the whole idea. Funding dried up.
So how did it recover?
Well, partly through the persistence of people like Hinton and Sejnowski in the 80s. They developed things like Boltzmann machines, which were multi-layer networks that could learn, kind of proving the earlier critiques weren't the end of the story.
Okay, so the ideas were still percolating.
They were, but the real resurgence, the deep learning revolution we see now, especially kicking off after 2012, that needed more. It was a combination.
A combination.
Persistence, yes, but also two other huge factors.
Yeah.
Big data.
Suddenly having massive amounts of data to train on.
Exactly, and vastly more computer power. Moore's law just kept delivering faster chips, making it feasible to train these much larger, deeper networks. Those three things came together.
The algorithms, the data, and the compute power. The perfect storm.
You could say that, and that storm led to some really impressive demonstrations, even early on.
Like what? Give us some examples.
Well, back in the 80s, there was a system called NetTalk.
NetTalk.
Yeah, it was a neural network that learned to read English text aloud. What was amazing is that it went through a sort of babbling phase, like a baby learning to speak.
No way.
Yeah, and it figured out pronunciation rules, even exceptions, just from the data. It suggested maybe these networks had a natural affinity for language.
Interesting. What else?
Then, in '92, TD Gammon, a program that taught itself backgammon.
Ah, yes, the board games, like Deep Blue and chess.
Similar time frame, but different approach. Deep Blue used massive brute force search. TD Gammon used backpropagation and something called temporal difference learning. It learned by playing itself millions of times.
I got good.
It got really good, beat world champions. But the most striking thing, it came up with creative new strategies, moves that human experts hadn't considered.
Wow, so not just calculation, but intuition.
Something like it. Hin argues it was genuinely more impressive in some ways than Deep Blue because it learned and generalized rather than just searching possibilities.
Okay, that distinction is important. What other milestones?
There's independent component analysis, ICA, an unsupervised learning technique,
Unsupervised, meaning
meaning it learns without labeled examples. ICA is famous for solving the cocktail party problem.
separating voices in a noisy room.
Exactly. You feed it mixed audio, it separates the original sources, and again, intriguingly, the components it finds look a lot like the simple cells in our visual cortex. Another bioconnection.
It keeps coming back to biology.
It does. Then, for handling sequences like language or time series data, a huge step was long short-term memory networks, LSTMs, developed around '97.
LSTMs. Heard of those. What problem did they solve?
They tackled the vanishing gradient or decay problem. Older recurrent networks struggled to remember information from far back in a sequence. LSTMs found a way to retain long-range dependencies.
Which is crucial for understanding sentences, right?
Absolutely. And that enabled things like pretty good machine translation and even image captioning, where an AI looks at a picture and writes a sentence describing it.
Without truly understanding the sentence?
Arguably, yes. More like learning complex statistical correlations between image features and word sequences. But the results became remarkably coherent.
Okay. And then there's the really flashy stuff. AI creating things from scratch.
Yeah, you're thinking of generative adversarial networks. JAMES.
JANs, right.
Yeah.
Creating faces of people who don't exist.
Exactly. That's a classic example. Jans use two networks, a generator creating samples and a discriminator trying to tell if they're real or fake, battling against each other.
An adversary.
Precisely. And through this battle, the generator gets incredibly good at producing realistic, novel outputs. Faces, art, music, learning from basically unlimited, unlabeled data.
Okay, so these breakthroughs, backpropagation, LSTMs, GNs, fueled by data and compute, they aren't just lab experiments anymore. They're everywhere.
Absolutely everywhere. Deep learning is embedded in, over 100 Google services alone?
Like what? Things we use every day.
Oh, yeah. Voice recognition on your phone. That's deep learning. Google Translate. Deep learning. Smart replies suggesting email responses. Deep learning. Even processing Street View images.
It's become invisible infrastructure.
Largely, yes. And Google went big on it early, hiring Hinton back in 2013. A lot of that focus was on self-driving cars.
Right, Waymo. You mentioned they have a fake town for testing.
A 91-acre fake town. They're serious about it. Projections are still debated, but maybe autonomous trucks within 10 years, taxis in 15?
Passenger cars, maybe 15, 25 years out.
That's one common estimate, yeah. It's a complex problem, obviously, dealing with the real world. But it's coming.
A massive change. What about healthcare? That seems like a huge area.
Huge. Deep learning is being used for diagnostics already. Analyzing medical images like skin conditions from photos, sometimes matching or beating dermatologists on certain tasks.
Really?
Yeah, based on huge data sets like 130,000 images for skin issues, or diagnosing sleep stages from sensor data very quickly with high agreement with experts.
In treatment.
Precision medicine, especially in cancer. Analyzing sequences from tumor cells, helping design personalized immunotherapies. It's moving fast.
Okay, transportation, healthcare.
Yeah.
What about finance?
Oh, it's been there for a while. A huge percentage of stock trading, maybe over 75% on the NYSE, is driven by algorithms, many using machine learning.
High-frequency trading and such.
Right, and fraud detection, catching suspicious credit card transactions in real time, that saves companies billions every year.
Okay, that makes sense. What about education? That feels very personal.
Yeah, it's interesting. You have MOOCs, these massive online courses like Learning How to Learn, teaching millions about learning itself.
Meta.
Yeah. But the more direct AI impact is maybe in personalized digital tutors. Systems that adapt to your pace, your learning style.
Like having a private tutor, but scalable.
That's the promise. It could free up human teachers for more mentoring, less repetitive drilling. And there are brain training games too.
Those actually work.
Some show promise. Neuroracers seem to improve multitasking in older adults. Fast Forward helps kids with language disorders. The potential for targeted cognitive improvement is there.
It's even learning to be social. You mentioned robots.
Yeah. Early examples like Ruby, a robot for toddlers. They found it could learn interaction strategies, like programming it to cry if its arms were pulled. It stopped boys from doing it, but made girls hug it. A learned social dynamic.
Wow, so AI is learning social engineering. That leads to the big question. How does this digital intelligence stack up against our own biological kind?
Well, our brains are amazing learners, right? Nature's champions, as the source says. We intuit solutions, learn generally. But the scale difference is interesting.
How so?
Our brains, maybe 100 trillion connections running on just 20 watts. Super efficient.
Like a dim light bulb.
Exactly. Now, a big model like GPT-4 might have only 1 trillion connections.
Fewer connections.
Fewer connections, yeah. But Hinton estimates it knows thousands of times more facts than any one person.
How is that possible?
Partly, it just reads vastly more text than any human ever could, but also digital networks can share information incredibly efficiently.
Share information.
Yeah, think about updating the model. They can transmit learned weights, gigabytes per second. Humans share knowledge through language, a few bytes per second. It's a huge difference in bandwidth.
So they can learn collectively much faster.
In a way, yes. But our brains have their own advantages. Incredible robustness.
Even though our neurons misfire sometimes.
All the time. Synapses fail like 90% of the time for typical excitatory ones, but we have massive redundancy backup pathways. We're fault-tolerant.
Built to last, even with flaky parts.
Pretty much. And that biological efficiency and robustness is inspiring new hardware, too. Neuromorphic chips.
Chips designed like brains.
Trying to be, yeah. Focusing on low-power analog circuits. Things like Carver-Mead's silicon retina or dynamic vision sensors that only report changes like our eyes do.
So biology informs the tech, and the tech helps us understand biology.
It's definitely a feedback loop. Which brings us to the future. What does Hinton see coming?
He paints a potentially positive picture, right? AI as assistants.
Yeah, he talks about a good scenario where AIs are like Super intelligent executive assistants, perfectly happy doing that job, no ego, no desire to take over or make copies of themselves.
It's just helpful tools.
Yeah.
But he also talks about sentience.
He does advocate for a broader view of sentience, suggesting advanced AI might fit into that category, which is definitely a contentious idea.
Highly contentious. And brings us straight to the risks and ethics. What are the main concerns highlighted?
Well, one big one is bias in the training data. It's almost unavoidable.
The AI learns the biases we feed it.
Exactly. Facial recognition struggling more with certain demographics because the training photos weren't diverse enough. That's a classic example. You can try to fix it, rebalance the data, but subtle biases can remain.
And what about the AI's goals?
That's crucial. The cost function, what you tell the AI to optimize for. If you just tell it maximize profit for loan approvals, it might learn to discriminate based on weird correlations in the data without any explicit rule saying discriminate.
Because discrimination accidentally correlates with profit in the historical data.
Potentially, yes. The issue isn't necessarily the AI being malicious. It's the objective we give it being too narrow or having unintended consequences.
And we often don't know why it made a decision, right? The black box problem.
Yeah, that's a real challenge. It's hard to get explanations. Hinton compares it to human intuition. We often can't fully explain our snap judgments either. They just feel right based on experience.
So maybe we'll just have to ask the AI.
He suggests that maybe someday a very large network could just tell us its reasoning. We can't rule it out.
What about the big one, existential risk? Is AI going to wipe us out?
Hinton, at least in the sources we looked at, seems relatively sanguine about that compared to other threats. He calls the risk from current machine learning relatively modest. Next to nukes or engineered pandemics, he thinks humans will adapt.
Adapt. We'll need to, especially with global competition. China's huge investment is mentioned.
Yes, they're training vast numbers of AI engineers, and they have a massive data advantage. That phrase, whoever has the most data wins, seems relevant there.
And the applications are dual use.
Very much so. Integrating AI into military tech, surveillance systems, censorship, even predicting potential crimes. It's a different context and set of priorities compared to, say, debates about science funding elsewhere. It fuels a very intense race.
So quite a journey we've covered. From those early philosophical divides,
Symbolic versus connectionist,
through the AI winter, the breakthroughs like backpropagation,
fueled by data and compute power,
to today's world, where deep learning is reshaping everything from our phones and cars to medicine.
And Geoffrey Hinton's story really threads through that whole evolution. Persistence when the ideas weren't popular.
Absolutely. And now, looking forward, we have these incredible capabilities, Hinton's vision of helpful AI assistance, but also these profound questions.
Consciousness, bias, fairness, the black box, the global race.
They're all on the table. So as we wrap up this deep dive, maybe the thing to ponder is, what stands out most to you from this journey?
And perhaps, how does thinking about these rapidly evolving digital minds make you think differently about your own intelligence? The biological kind. Lots to chew on there.